Hi Math 215 students. In this first video for section 2.2, we'll have a bit of a prologue to the concepts in this section. We've titled this, You Can't Divide by Zero, or Can a Matrix Have a Reciprocal? There aren't any outcomes for this video. We just want to introduce some ideas that will be useful to us. And so I want to back up a little bit and take a look at some of the most simple algebraic equations you can run into. And this is just a constant times your variable equals another constant. So if you were to solve 7x equals 21 or 26y equals 52, most of us would, without thinking, just say we'll divide both sides of the equation by 7 or by 26. And dividing is something that's very useful to us. You probably learned that dividing is the same thing as multiplying by a multiplicative inverse. And so in particular, if we wanted to, we could think of multiplying both sides of the first equation by 1/7. 1/7 is the reciprocal of 7. And what's nice about 1/7 is that if you were to multiply it onto 7x, well, first off, the associative property means you can regroup the multiplication there and put the 1/7 and the 7 together first. And we can certainly multiply 21 by 1/7. But on the left-hand side, 1/7 times 7 gives us 1. And 1 times x is just x. And so at this point, we know that x should equal 3. Right? Now, if you're used to thinking of this in terms of division, you would get that answer almost instantaneously if you knew that 21 divided by 7 was 3. But it will be helpful to us to take a look at these steps. We multiplied by the reciprocal, or the multiplicative inverse, 7. And that created a 1, and 1 was what we needed to find out what x was. Okay, similarly with the second equation, we would multiply by the reciprocal of 26, and when we do that, again, on the left-hand side, the multiplication can be grouped so that you're multiplying 26 and its multiplicative inverse. That creates 1, and 1 times y is y. So we know that at this point, y is equal to 52 divided by 26, which is equal to 2. Okay, now in both of these equations, we solved by making a 1 on the left-hand side. And we did that by multiplying by the reciprocal, or the multiplicative inverse of the constant on that left-hand side. Now, at this stage in your mathematical career, this is all automatic. You do this without thinking. But we're going to be exploring this idea and how it might be useful in solving similar equations involving matrices. When we talk about dividing or multiplying by reciprocals, we need to recall a fact that was drilled into you from the first time you learned about division, and that was this: you cannot divide by the number 0. Now, 0 does not have a multiplicative inverse. And to see why that is, you could just imagine, well, what if it did? What would happen? What would division by 0 give you? And so we'll start in our first bullet point here by just taking a look at, well, if x was the reciprocal of 0, then what would happen? And if I take a look at that, if I were to start with this equation and multiply both sides by 0, I might get the equation 0x equals 1. However, 0x equals 1 doesn't have a solution. There's no real number that x could be that could make this work, because 0 times any real number is equal to 0. The right-hand side is equal to 1, and 0 and 1 are never the same. So this equation has no solution for x. There is no real number that is the reciprocal of 0. Now, this equation has a problem because the right-hand side was not 0. If we did let x be 0 over 0, then we run into not the same problem, but now we find another problem. If x is supposed to be the result of dividing 0 by 0, then what should x be? And as you take a look at this equation, you see that actually anything is a solution to that. X could be 7, or x could be 1, or x could be 0. There are infinitely many possibilities for that x. There are infinitely many solutions to the equation that we get out of the situation where x equals 0 over 0. Okay, So this is one reason why we often refer to these kinds of divisions as undefined. There just is not a single correct answer in these situations. Now contrast that with what we just saw for these equations that started with a number that did have a multiplicative inverse. You're able to solve for the x, and there is exactly one solution for x or for y. That's not the case when we are solving equations that involve a zero in front. Now we're going to see something similar when we talk about matrices, and in particular, we're going to see that you cannot divide by some matrices, and in particular, the matrix 1, 2, 3, 6 is one that you cannot divide by. And to see that, we're going to answer a few questions. First, if x is an unknown matrix, and you had the equation this matrix times x is 0, 1, 3, 2, then what should the unknown matrix x be? The second question is the same setup. It's just that we're setting it equal to 0, 0, 0, 0. We want to find out what is the unknown matrix x. And then the third question reminds us some of the things that we talked about in the cautions about division, cautions about matrix multiplication rather. If 1, 2, 3, 6x equals 1, 2, 3, y, can you cancel both sides out and say that x equals y? Well, we'll see that something interesting happens in that situation. Let's take a look at the first question. The first question was, if you want to set 1, 2, 3, 6 times some unknown matrix equals to 0, 1, 3, 2, and if you want to solve for x, how would you do it? Now, this is the scenario where if we could divide by matrices, it would be just nice to divide both sides by 1, 2, 3, 6, and if we knew what that meant, we would have a solution for x. But we don't know what it means to divide by matrices at this point. So we're going to solve this in old school way. We're just going to suppose that x is the matrix with entries A, B, C, D, and then we're going to multiply this matrix onto A, B, C, D, and we want it to produce the matrix 0, 1, 3, 2. Okay, so what we have on the right are the equations that would pop out of this. For each of these entries 0, 1, 3, 2, I have taken the corresponding product of 1, 2, 3, 6 together with this ABCD matrix and set them equal. So for the top left entry, I should get a 0, but I would get 1 times A plus 2 times C. And so I get 1A plus 2C equals 0. And as you take a look at the other three positions and the matrix multiplication that would happen if you were to multiply 1, 2, 3, 6 onto x, we get these other three equations. Now this is a system of 4 equations with 4 variables, so we know how to solve those. We will go ahead and just form an augmented matrix. The first equation gives us that top row of the matrix, and the other 3 equations give us the other rows of this matrix. It's an augmented matrix, so in this video I'm going to use a vertical line to separate the right-hand side column from the coefficient matrix. Now if we were to row reduce this, you see that we do have a 1 in the pivot position in the top left corner, and I can multiply the row 1 by -3 and add that to row 3 to cancel out the 3 there. And similarly, I can clear out the bottom row as well. It's just that when you do those row replacement operations, we'll end up with 0, 0, 0, 0, 3 and 0, 0, 0, 0, minus 1. And we know that this is a bad setup. We know that there will be no solution to this system of linear equations because you do have a row with all zeros except for a non-zero entry in the last column. And we know that that leads to no solution. Well, what that means then is that there are no choices for A, B, C, and D that will work in all of these equations. And that tells us that there is no matrix X that makes this equation true. Well, that's kind of like this first setup. When we were talking about dividing by 0, we ran into equations where there was no solution for x. Now here we're talking about matrices, but the same result is happening. There is no solution for x if you start with the matrix 1, 2, 3, 6, multiply it by x, and then set it equal to some other matrix on the right. Now let's move on to the second question. Well, what happens if you just put the 0 matrix on the right? Couldn't you find a solution for x in that situation? Well, let's start off the same way we did before. We're going to let x be the matrix A, B, C, D, and again we'll have these 4 equations. This time, because we're setting it equal to the 0 matrix, we'll have 0 on the right-hand side of each one. And as we set up the augmented matrix from before, you can maybe see what's going to happen. As we row reduce, the bottom 2 rows just completely cancel out. We end up with just rows of zeros there. And so there is no problem. We don't run into the situation we had before of a 0 row ending with a non-zero term. In fact, this thing has a solution. This system does. 1 and 1 show up as in the columns corresponding to A and B, so those are pivot columns. But the columns for C and D don't have pivot positions. This system has free variables. And so we know that, in fact, there are infinitely many solutions for this matrix X. There are infinitely many choices of A, B, C, and D that would work to satisfy this equation. Now, infinitely many solutions was the situation that happened when you tried to solve 0x equals 0. And so we do see a correspondence there as well. And so, so far, having 1, 2, 3, 6 as the matrix is starting to behave a lot like the situation where you have an equation with a 0 on the left-hand side, 0 times a real number. Now, finally, this last bullet point, as we said, kind of goes back to one of the cautions we saw when dealing with matrix multiplication. The idea that you need to be careful when just canceling out a coefficient on the left and the right. Is it true that if 1, 2, 3, 6x equals 1, 2, 3, 6y, then we can forget about the 1, 2, 3, 6 and just say that x equals y? And as we take a look at this, we'll actually go back to our work on the second question and go a little bit farther with it. So you'll remember there we were trying to solve 1, 2, 3, 6 times x equals the 0 matrix. We saw that there were free variables. In fact, we can write the parametric description of our solution set in this way. C and D will be free variables. And then from the first 2 rows, you see that A is equal to minus 2C and B is equal to minus 2D. And so that tells us that if we chose C and D to be 5 and 10 or negative 15 and negative 20, we could figure out what A and B should be, and we'll get a couple different possibilities for that matrix X we're timesing by. In fact, for any choice of C and D, you get another matrix that makes the equation true. But let's take a look at it this way. 1, 2, 3, 6 times this first matrix gives us the 0 matrix. 1, 2, 3, 6 times the second matrix also gives us the 0 matrix. So in particular, 1, 2, 3, 6 times each of these matrices give us the same answer. But you cannot cancel the 1, 2, 3, 6 from the equation because negative 10, negative 25, 10 is not the same matrix as 30, 40, negative 15, negative 20. And so what we've done is give an example of where cancellation will not work if 1, 2, 3, 6 is the matrix you've got on the left. So we have some resemblance between the matrix 1, 2, 3, 6 and the situation we run into with dealing with multiplication with 0. On the other hand, some division problems are simple, right? The ones we started with, where you have a number that's not 0 on the left, these are super easy to solve. You solve equations like this by multiplying by the reciprocal, or the multiplicative inverse, of the coefficient on the left. You do it by making a 1. Can you do the same thing for matrices? Well, let's take a look at one particular matrix, the matrix 1, 2, 3, 5. So it's almost the same matrix we were looking at before. We've just changed the 6 in the lower right to a 5. And if we take a look at this matrix, take a look at what happens if you were to multiply by this matrix in blue, -5, 2, 3, -1. Now, I haven't explained where this came from, but just take a look at these facts. If you do multiply 1, 2, 3, 5 by that matrix, you should get 1, 0, 0, 1. Whether you multiply the matrix on the blue on the right or whether you multiply that on the left, in each case you get out the identity matrix. Remember, the identity matrix has a diagonal of 1s and then 0s everywhere else. And that's what we have here. Now, the thing we saw about the identity matrix is that when you're multiplying matrices, the identity has the property like 1. 1 times any number leaves the number alone, and the identity times any matrix leaves the matrix unchanged. So just like 1/7 was useful in solving equations involving 7, maybe we can use this -5, 2, 3, -1 to help us in solving equations that involve 1, 2, 3, 5. And let's try and do the same thing we do in the 7x equals 21 equation. Okay, there we start by multiplying both sides of the equation by the multiplicative inverse of 7. We group the 1/7 and the 7 together, and that creates 1, and 1 times your variable is just your variable. So we're going to take 1, 2, 3, 5. We're going to take the matrix we were just looking at and do the same thing. We'll multiply both sides with that. Multiplication rules allow us to group those together. And on the left, when you do multiply these together, you get the identity matrix. And we know that whatever x is, the identity times x will just give us x. On the right-hand side, though, we can do some matrix multiplication. -5, 2, 3, -1 times 0, 1, 3, 2. Doing that matrix multiplication gives us 6, -1, -3, and 1. And in fact, if you were to check your work, taking this matrix and plugging it in for x, you'll see that actually it is the matrix that makes this equation true. So in this equation, just like in the first one, we solve it by making a 1, but in this situation, the 1 we're talking about is actually the identity matrix on the left-hand side. This -5, 2, 3, -1 is acting like a reciprocal of 1, 2, 3, 5, or better said, it's acting like the multiplicative inverse. Okay, so as we summarize this prologue video, we see that there are some differences in the behavior of multiplication and equations when you're solving with the matrix 1, 2, 3, 6 or the matrix 1, 2, 3, 5. The differences seem to come from the fact that 1, 2, 3, 5 had an inverse, something that you could multiply that matrix by to create the identity matrix. Now, 1, 2, 3, 6 does not have an inverse for some reason. And what we've shown in the video is actually enough to see this. If 1, 2, 3, 6 did have an inverse, then you could solve some of those equations that we saw didn't have solutions or didn't have a unique solution. So 1, 2, 3, 6 does not have an inverse. We're going to talk about why, but this is actually one of the big questions. We have two big questions for us. As we go through section 2.2, we're going to be talking about which matrices have inverses and which do not. Can you tell just by looking at our matrix? Is there a way I could look at these two matrices and decide that the second one had an inverse and the first one did not? How do you do that in general? Second of all, if you know that a matrix has an inverse, how do you find the inverse? Where did this matrix -5, 2, 3, -1 come from? Is there any procedure or rule for finding the inverse of a matrix if there is one? Well, we'll answer both of those questions. Stay tuned and we'll see you in the next video.